Okay. So it's starting to look like there's not a bug in the code that I've been tracking down. Instead, the convergence rate is just so terrible that it appears not to be working. That seems reasonable. So what to do? Well, there's this paper by Condat. And if we go to section 5, This paper presents an optimization problem, and here he's extending it to one of this form. Here we have a sum of functions applied to different linear operators of our optimization variable. So this is a form that we can use to solve our problem, and so maybe this approach, this algorithm by Condat, would work. And so I could dig into this for a while. But that's not what we're going to do today. Instead, what we're going to do is just assume that psi is orthogonal. Okay? So for the inputs, for the optional inputs right now, a function handled to an orthogonal sparsifying transformation. And this is going to solve everything for us. Because then the proximal operator of S becomes simple. The proximal operator of F becomes simple. So let's take O psi out of there, because we can't handle anything other than O psi right now. Okay. Okay. So now we can assume psi is orthogonal, right? So we are going to get rid of a lot of stuff. We have been debugging this stuff for a long time. Okay. Oh, this assumes... Yeah, this assumes that we're using S maps with lambda. Where does psi get used? V psi. Here I can just do this. Oh no, I see. All right. Why do we have this? Because we set O psi equal to true for the default psi, so we didn't need that. Okay. Excuse me. So this is the case if sigma is equal to 0. Am I calling it sigma? If now I want a bound. I see, so I wasn't there yet. Okay, so for n coils equals to 1, there we go. Okay, so that's broken. Why is that broken? And thresh weights B. This is what we're minimizing. It's like we're doing the sparsity term on the wrong thing, right? BCS is equal to psi F inverse MCT. Let's find that. We're doing psi. Oh, we changed what psi is to be the identity matrix, and I don't want to do that. Okay, so that's the result that we were getting before. I think that's working. Okay. So if we don't have an epsilon, then that. Otherwise the problem becomes totally different, doesn't it? We want to minimize the L1 norm of psi x subject to mfx minus b less than or equal to epsilon. Okay. So apply A is going to equal apply MF. Well, yeah, apply MF. Is there an apply MF? Do we have such a thing? No. I forgot to tell my incredibly eager audience that I am streaming. Okay. Let's put apply MF there. Apply MF there. Does this get used in checks? We're not checking apply MFS? Huh. Let's do checks. Apply MF. It passes. It's not surprising, but I'm just happy to have it done. Okay, coming back here, we're now going to implement compressed sensing using this problem. Apply A is equal to apply MF. F is equal to at in the L1 norm psi, I guess V psi in. Do we have a V psi? We do. Prox F so it's going to be prox L1 complex. But we're going to do a composition. Prox compositionifying. In V psi 0, 1. I think that's right. So this performs the composition of prox L1x with the linear transformation psi, which we're putting there. Mm-hmm. No, yeah, okay. G is equal to at in the norm of in minus B 2. No, it's not. It's not. It's equal to the indicator function of that. Zero epsilon. I think that's how we do it. S, yeah, in S, and S is a 2-element array, minimum, maximum, great. And then, now we need the prox G. That's going to be projected onto a ball in epsilon. That's the L2 norm. Hopefully P is 2 by default, and it is. Think it works? We need to supply epsilon, don't we? Do I have a noise bound? No. I just have noise coordinates. Okay. Where's the full recon? Image true is there. I don't want image true, I want coil recons. Okay. Now the noise is coil recons. Noise chords, I never remember. 1, 2 noise chords, 2 noise chords, 3 to noise chords, 4. What are the noise coordinates? Oh, 193. Okay. So that's not how it goes. To 3, 2 to 4. It's going to be it's supposed to be in the upper right-hand corner. So this is actually 2 to 4, 1 to 3. Okay. That looks like noise to me. Looks like the anti-aliasing filter is helping us out a bit at the top. So instead of 1, we're going to change that. What data case are we working with? 19. Wait, no, data case 9. Okay. We'll do like 5. But to actually do that, now we got to load the data. It's so annoying. Okay, the variance, okay, it didn't take long at all. Noise chords, 5, right. I believe that noise chords should start at 5 in the vertical direction, and it does. Great. Okay, so now if we look at the variance of the noise, okay, now we're back to this stuff. We're revisiting old wounds. What I wanted to do is NB. Oh. Okay, so indicator function. Epsilon NB times epsilon. So I'm just going to do this. Noise divided by NB. That's the thing. And that's equivalent to take the NB from here and multiply it times here, and square root both sides. Okay. What is the L2 norm of noise squared divided by NB? Num L noise. 3.4765 times 10 to the negative 11. What's the noise var? That didn't help at all, did it? 3.4765 times 10 to the negative 11. Great. Represents the variance of the noise. Okay. Now here, we don't need to do this again. We can just do that. Oh my gosh. Already did that. All right. Guess I'll do this. Now if we come down here, we got noise, no, epsilon is noise var. We are passing epsilon in. Unrecognized function of variable x naught. Yes, okay. Let's see what x naught is. Yeah, it's the least square solution. That's what I expected. Why? Why? Not enough input arguments. I see. 295. Let's do that. What's the problem now? Arrays of incompatible size. Okay, that's going to be a bummer. Prox F. Yep. Let's see what happens here. So X here is of size image. So I think I just need to change that to psi, though I'm not sure. Yeah. Unrecognized variable function psi? What? Oh, right. Because psi is already a function handle. That's my guess. Don't know that for sure, but that's my guess. Looks like I was right. That looks terrible. There is a bug. Let's not panic just yet. V psi. Okay. We've seen that result before. How did we fix that? I don't remember. Just to be sure, like prox in psi 01t. Prox in psi 01t. And the wavelet transform is orthogonal, so that makes this 1. Let's make epsilon tiny. Where is that image coming from? Oh, I see. Okay. All right, and that's the terrible image. Why is that? You're applying MF. I don't remember using this. It is possible that this is just like broken. Oh! think I need to do minus b plus b. If you're taking the function ax plus b, there's a plus b on the inside. We're doing minus b, so there's going to be a minus b on the inside and a plus b on the outside. Now, this is not going to shock you, but I do not like that result. I don't like that one either. Okay, nothing's changing, it seems. Oh, or is it? Wait a second, this is very confusing to me. Okay, let's see if any power of epsilon will solve this issue. Hold on, so negative 20 to negative 5. To negative 5, yeah. Okay, that looks like a data constraint of, hard data consistency. So does that. So does that. Leave this one around. Those two look exactly the same. (14) and 18 look exactly the same. 13 is still not changed. Is there a bug in this? There's a square root of epsilon there. So it looks like we're actually using epsilon. Okay, things are changing. Between -18 and -7, things are changing. Not much, but a little bit. Oops. Just delete that one. And that looks terrible. Okay. -8 is slightly better than -18, and -5 is really bad. The big conclusion here, though, is it's not giving us a good answer. I don't know why that is. Am I misremembering what I can make the sample fraction with compressed sensing alone? I don't know. We're going to have to investigate this next time. Thanks for stopping by.